that's non-commercial, including ones that run on software-defined radios like Jiao Xiandun's SDR Bluetooth. It's just a narrowband sniffer in a trench code. So what about a multi-channel approach? We've got things like HackRF, BladeRF, USRP. They can sit on a big chunk of spectrum at any given time. They can listen on more than one channel. And you can actually get multiple Bluetooth advertising channels this way, and even capture some active connections. So then you might be asking yourself, well, why not just sit on all 80 Bluetooth channels at the same time? The answer is money. The cheapest software-defined radio up until now that does this costs about $8,000. It's an Edis USRP X300 series. And if you're looking at specialized Bluetooth devices, or specialized devices for just sniffing Bluetooth, now you're talking like 20, 30 grand. But I'm happy to report, as of this talk, sniffing Bluetooth is not hard anymore. And it's all thanks to this guy, Rob Gilduda, the guy who created the BladeRF. He recently released an update to the firmware that gives it 122.8 megahertz instantaneous bandwidth. All we really need is 80 megahertz, technically 96, but we don't need all that. But the BladeRF can do it. And instead of having a narrowband sniffer that hops around, or a wideband sniffer that sits on just a chunk of the spectrum, now we have a super ultra-wideband sniffer that can sniff all of Bluetooth at the same time. But that's not all. I actually integrated it with Wireshark. So as of today, if you install my tool, open up Wireshark, scroll down to the bottom of your interfaces list, you'll see ICE9 Bluetooth, that's the name of my sniffer, with a list of any supported software-defined radio you've got connected to it. Yeah, thank you. You don't save your applause, please. Click on that guy. You get some options for configuring what channels you want to listen to. Click Start, and bingo, you get Bluetooth packets right in Wireshark from a software-defined radio. It works with a HackRF, it works with BladeRF, and it works with the USRP B200 and B210 series. They're all supported in Wireshark today. And that's pretty much it for the beginning of the talk. This is all you need to know. If you want to start using Bluetooth sniffing right now, and you've got a BladeRF, a HackRF, or USRP, scan that QR code. It'll take you to that URL right there. Download and install it. If you've got one, I encourage you to install it right now. It's super easy. It has very few dependencies. It builds like no problem. With that, I'll leave this up. I see a lot of people taking pictures. It's a lot. So with that said, I'd like to segue to the true title of my talk, which is actually everything I wish I had known about software-defined radio since 2013. And the reason I put 2013 is that's when I got my first software-defined radio, a HackRF Jawbreaker. This is the beta of the HackRF 1 that was released as a Torcon badge of all things. And when I got it, I did all the usual type of stuff. I started listening to FM radio stations. This is basically the hello world of software-defined radio. If you've got an RTL SDR, you've probably done this. And I started digging a little bit deeper. And the first direction that you usually go when you dig deeper is new radio, which is fine. It's a flow graph-based system. If you've never used it before, it can be a little confusing. But basically, you've got data sources, data sinks, and filters that can alter the data as it goes through the graph. And this is a really somewhat intuitive way of building a radio receiver. The problem is, anytime I tried to dig a little bit deeper, things got kind of weird and intense. The flow graphs sort of grew out of control, and everybody explaining them sort of ended up looking like this. It wasn't great. So rather than go down the rabbit hole of GNU radio and how to understand all that, I'm going to start at the very basics. What is RF? It's a borderline philosophical question, right? It has an easy answer, which is that it's a burst of energy at a given frequency. Not super helpful. The other way you can look at it is, well, literally look at it. If you're looking at me right now, you're looking at RF. Visible light is just very, very high frequency RF. We're actually interested in much lower frequency RF, around the 2.4 gigahertz range, which is what comes out of Bluetooth. But I like to think of RF an analogy or actually let's build a simple RF system so we have something to talk about. So imagine you're building a radio station. You've got a microphone, it's connected to a broadcast tower, that broadcast tower spews out RF. On this end of the connection, you've got an FM radio. So when the DJ announces the next big hit, your radio picks up that signal, turns it turns it into an audio signal, and you're able to hear it. Well, what if instead of a radio, we use a software-defined radio to pick it up? That will output digital IQ. What is digital IQ? The best way I can explain it is by analogy to another signal source you've probably heard before, which is to say sound. When sound waves travel through the air, they're a compression wave that strikes a microphone's transducer that gets turned into a digital audio signal. So in this regard, you can think of digital IQ as the RF analog to a digital audio signal. And a software-defined radio is basically just a microphone for RF. And how do you begin to analyze that? One way is to look at signals in the frequency domain. This is the audio spectrogram of somebody saying a few words. And if you were going to try to analyze this using computers, you can already kind of come up with some ways you might do that. Like you can follow some of these higher energy portions of the signal and maybe track the frequency that way. What about if we look at an RF capture of the same thing? This is an actual capture of the FM radio spectrum around my house. And if you zoom in on it, you'll see individual radio stations are actually just little sound waves that are modulated in the frequency domain. That's why it's called frequency modulation. The frequency of the signal varies according to the original sound wave. So what happens when we bring a software-defined radio into the picture? This is a simplified model of a software-defined radio. It all starts with an analog RF front end and an analog to digital converter. This is really critical. The signals that are coming in are going to be continuous analog signals that look like this. They have infinite precision in time, infinite precision in amplitude. What we're going to do is we're going to digitize those in time and frequency and turn those into IQ, and we're going to process those. What does this digitized IQ look like? It's actually just a sequence of complex numbers. You might be thinking to yourself, what about complex numbers? Why are they complex? Why do I even care? The answer is they're just like a regular audio signal that has a stereo track, where there's a left signal and a right signal. Except now, instead of being the audio that's going into your left ear and the right ear, it's the real and the imaginary part of the signal. Don't get hung up on imaginary. All you have to do is think about these complex numbers as two-dimensional numbers. And at a given time, you might have a sample that's right here on the real imaginary plane, or XY plane, if you just want to think of it that way. And a moment later, the signal might be over here. And then the signal's down here. And when the RF is floating through the ether, you can just think of it as a little vector spinning around the origin, and that is carrying the information that we want to understand. So what do we do with this complex sequence of complex numbers? The answer is enough to strike fear in the hearts of undergraduates everywhere. DSP. What does DSP stand for? Is it perhaps Deep Secrets of Pandora? I'm not sure about that. Dizzying Spectrum Puzzler? I think we're getting a little bit closer. Yes, digital signal processing. That's how we turn our spinning IQ signal into Bluetooth. So you may be thinking to yourself, this is all great, but how do I sniff Bluetooth? Isn't this a talk about sniffing Bluetooth? The answer is it's super duper simple to sniff Bluetooth. You tune your radio to 2440 megahertz, that's smack in the middle of the Bluetooth spectrum. You set your sample rate as high as it'll go, and you click the capture button. And what do you get when you do that? You get an IQ file that looks something like this. This is a tool called Spectrum. You can use it to open files that you capture from software-defined radios. Super duper useful tool. All the people who had their phones out earlier taking pictures, take a picture of this one too. Because if you're interested in getting into software-defined radios, it's a really powerful tool. And you can see time is on the x-axis, frequency is on the y-axis. And all of these little bursts of energy here, the little red or darker green and red areas, those are all Bluetooth packets. And what's more, as you look at these packets, you can already start to see that they're separated into discrete channels. So what do we do with those discrete channels? Well, if we're going to listen to all channels at the same time, we need a way to break them up into individual channels so we can process them separately. And we do that with something called a polyphase channelizer. The previous version of this talk had a whole bunch of stuff about Armstrong receivers. I just cut all that out. Polyphase channelizers are a magical, modern DSP tool that will take a whole bunch of data and split it into individual channels for you. And for now, if you want to learn more, I would recommend this book by Fred Harris, In Fred We Trust. This man's name is all over signal processing. If you've ever heard of a Blackman-Harris window, he's a co-inventor of it. Almost all modern polyphase software-defined radio stuff is Fred Harris. So let's just imagine for now, take me on faith, that a polyphase channelizer gives us what we want. It gives us individual channels out of this huge wideband capture. So we've got our individual channels. Where do we go from here? How do we get the Bluetooth out of this big sequence of complex numbers? We're still dealing with complex numbers here. Well, if we zoom in on an individual packet, what we'll notice is that the amplitude of this packet is something that we can calculate really, or amplitude of each sample is something we can calculate really easily. It's just the square root of the real part squared plus the imaginary part squared. And in fact, because we're just comparing these, we don't even need to take the square root. So what we do is we plot that amplitude over time, and you see an obvious rise in amplitude when there is a signal present versus when there's just background noise. So what we do is we draw an arbitrary line, we call it a squelch, and anything above that squelch, anything that breaks squelch, as the parlance goes, is considered a packet. And we grab that, we tag it as a burst. We also keep track of the length of that burst. That's going to come in handy later. So, zooming in on our burst, if we're looking at it in Spectrum, we can right-click on it, click or aim at Add Derived Plot, click Add a Frequency Plot, center the little bar on the capture there, and you can see at the bottom, that looks like a digital data. We haven't even written a single line of code, and we're already looking at what looks like ones and zeros. You can actually decode this by eyeball if you needed to. But we don't need eyeballs, we have computers for that. Math alert. I'm going to give you a little bit of details on some of this stuff now. Frequency demodulation. What is it? How does it work? If we're trying to write code to do this, we're obviously not going to write code. We're not going to just keep using in Spectrum to decode hundreds of packets, maybe thousands of packets before you finally sit down and write code. I don't know anything about that. But instead, we're going to write code to do this. How do we do frequency demodulation? This is going to sound a little bit scary, but trust me, it's not that big of a deal. Frequency demodulation is just measuring the change in the phase angle of your samples. So basically, how fast is your vector spinning? If it's spinning really fast, you're going to have a positive frequency offset. If it's spinning backwards, you're going to have a negative frequency offset. This is all there is to frequency demodulation. In fact, this is the equation for it. You just take the R, which is the angle of the current sample multiplied by the complex conjugate of the previous sample. You don't have to understand why it works, just know it totally works. And if you write this code, you will get data that looks something like this. There's our data from the previous image. It's just now been pulled into the new plot so we can look at it more carefully. So far, everyone with me so far? Anyone lost? Go back one slide? Sure. Somebody's taking notes here. This will be on the test. And so the other interesting thing I forgot to mention here is that when we take the angle of this complex number, the angle is a real value. So now we've gone from complex numbers that have two dimensions back into real numbers that have a single dimension, which is how we can create a plot like this. If you tried to plot the IQ data, it would just be a bunch of waves that don't make any sense. But once you do this math on it, you take the phase angle, the change in the phase angle, bingo, we've got ones and zeros here. Now the first thing you might notice about this graph is that it's slightly offset from zero. This is called the carrier frequency offset, and this is a result of the center frequency of the transmitting radio being slightly different from the center frequency of the receiving radio. This is impossible to avoid. We want to have variances in temperature, crystals, all sorts of things. We have to correct for that. The other thing you're going to notice is that the values range from roughly -0.2 to 0.2. This is proportional to the FSK deviation. It's in some really weird unit like radians per sample, but you can turn it back into a frequency if you want. So I looked through literature on how to try to solve this problem and correct the carrier frequency offset and the FSK deviation. We want that value to swing from -1 to 1 because our algorithms just work better with that. I came up with something called the improved median method, which improves on the median method that Mike Osman put together in whole packet clock recovery back in GRCon 16. The way this works is you take the first n points of your signal, you bucket them into positive and negative. If either of those groups is empty, reject the packet. It's just noise. First, you take the max of the median of the positive points, the min is the median of the negative points, and you find the midpoint of those. This is the carrier frequency offset. Then we take the max minus the midpoint divided by 2. This is the scaling factor that is the FSK deviation. You subtract the midpoint from all points, centering them about 0. Divide all the points by the scaling factor, scaling them to -1 to 1. You end up with a signal that looks like this. It's centered about 0. The frequency swing is about -1 to 1. This is our normalized corrected packet. This is something we can work with to actually decode into 1s and 0s. Now, before I get there, something interesting I noticed was that if you take the carrier frequency offset and plot it against the FSK deviation for all these packets, you start to notice patterns. In fact, you see a group of a cluster up at the top of classic Bluetooth, another cluster at the bottom of classic Bluetooth, and then here in the BLE section, we have a few clusters of various BLE devices. These are all actually individual devices transmitting. These are physical properties of the receiver that we can plot and use to track individual devices. I'm not the first person to come up with this. Somebody wrote at least one paper on this called Evaluating Physical Layer BLE Location Tracking Attacks on Mobile Devices. And this is really interesting because no matter what Bluetooth security and privacy features you have, if your device is transmitting, it's trackable this way. So ultra-paranoid people, maybe keep this in mind. Moving on to clock recovery. This is the next phase in the single processing chain. This is how we go from these random sequences of numbers kind of going up and down into perfectly centered bits. Because we don't know the exact clock frequency of the transmitter. We know it's about 1 megabaud because it's about a 1 megasample per 1 megabit transmission, but we don't know exactly. How do we do this? I punted on this. At this point in our processing chain, we have 2 samples per symbol, which means we could just take every other sample and use that as our symbol. I recommend using a polyphase symbol sync. I actually had a version of this slide that talked all about it. I never got it working right. It's actually really hard to tune those. So for now, I just take every other bit, every other sample, which leaves us with a big old pile of bits that looks something like this. We don't know where the start of our packet is. We don't know where the end of our packet is. We don't know where any of the information, the interesting information in our packet is, but we have bits. We're getting closer to having Bluetooth packets. Now it's time for us to look at the structure of a Bluetooth packet. This is a BLE packet. They all begin with an 8-bit preamble, which is either 010101 or 101010, followed by a 32-bit access address, a 16-bit header, optional data, and a 24-bit CRC. Now, when a normal Bluetooth device is part of a connection, it knows the 32-bit access address of the other end of the connection. So it's able to correlate on that access address in order to pick up the signal from the noise and know where the packet begins. We don't know that. We're trying to promiscuously sniff all Bluetooth connections in the area. So we don't have this information. You may be looking at the preamble thinking, well, I can look for 010101 or 101010 and just figure my packet starts there. Unfortunately, that does not work either because these are very susceptible to noise. A lot of times they will just not come through correctly. Instead, we're going to zoom in on the header. If you look at the header, it's made of 2 8-bit fields. One is flags, the other is the length. Remember earlier when I said we have the burst length? Well, if we go through the packet and start measuring lengths relative to the burst length, we can potentially figure out where our valid packet begins. So let's look at this somewhat true experience. Sorry. Let's look at this somewhat true example. We're going to assume that our burst here is 78 bits. These are the bits that we have. What we're going to do is we're going to assume the packet starts right at that little red caret. And if that's the case, these underlined red values are going to be the access address. This is our candidate length. And finally, so our candidate length here, let's calculate it as 138. How does that compare to 78 bits? Too long, not accurate, not the beginning of our path. Let's move forward one bit. So our new candidate length, our new candidate access address is one bit further. Our new candidate length is one bit further in the packet. In this case, our candidate length is 78, which is really close to 74 rather, and it's really close to 78. So we're going to remember this one. This is probably the start of our path. But just for completeness sake, we're going to go ahead and try one more bit further ahead in the path. So move up one bit, our candidate access address is up one bit, candidate length is up one bit, 15, I don't think so. So our candidate length right here of 74 is probably correct, which means we know the start of the packet, we know the access address. We can start stuffing it into PCAP. That's it. We're almost done, right? One last step. We have to get it into Wireshark. I promised you Wireshark, and they deliver on that. Back in 2013, there was a subsystem in Wireshark introduced by these two clowns. You might know the first one is Draghorn of Kismet, as well as yours truly, Mike Ryan, the Bluetooth expert, or Mike Bluetooth, as somebody called me once. I'll take it. That's what we look like today. The way you approach it is you implement command line flags, output PCAP file to a pipe on the command line, you get Wireshark for free. Seriously, that's it. That's how you get Bluetooth and Wireshark. So with all that said, I'm going to describe the full architecture of my Bluetooth sniffer. On the input, you get n megahertz of RF, where n can be anywhere from 4 megahertz all the way up to 96 if we're doing all channel sniffing. That gets plugged into a polyphase channelizer, which I described earlier. That splits off the n megahertz into n streams that are 2 megahertz wide each. Why 2 megahertz? Because our friend Nyquist tells us that if we want to get a signal of 1 megabit out, we need twice that frequency of sampling, so 2 megahertz. These get passed into burst catchers that are looking at the amplitude of the signal, tagging bursts. Those bursts get sent out into a queue, and that queue is serviced by a burst processor. And in the burst processor is where all the FSK, Bluetooth, and PCAP happens. And that's where all of our Bluetooth comes out. You may be looking at this diagram and saying, Mike, you only have a single burst processor. Surely that's your bottleneck. To which I say, no, that is actually not the bottleneck. The bottleneck is the polyphase channelizer. Remember, we've got data coming in here at up to 96 megahertz. That means we only have a few dozen nanoseconds to respond to each individual sample before moving on to the next one. So let's zoom in on a polyphase channelizer. You're probably looking at that thinking, what the fast Fourier is that? It's actually really simple how you implement it. I'm breaking the cardinal rule here, and I'm including some code on the slides. But it's because it's really simple code. You just go from 0 to 95, push a sample into the buffer in reverse order. You start at the bottom, work your way up. Again, don't ask me why. It just works. Trust the math. You load samples into a buffer, and you compute the dot product of that buffer with the taps of a filter. Finally, you take the inverse FFT of that input buffer, and the output of the inverse FFT is the individual channel signals. How does a dot product work? Well, you've got a sequence of complex numbers at the top, a sequence of real numbers at the bottom, which are the filter taps. What you do is you multiply the complex numbers by the real numbers, add them together. So you're going to multiply and then accumulate. Multiply and accumulate. Remember that. How do you multiply a complex number by a real number? And then add them? I'm going to skip right through all this math, but you can group the real parts and the imaginary parts together and just compute the multiply accumulate of the real parts separately from the multiply accumulate of the imaginary parts, which looks something like this. This is not what the code in the Reduce looks like, because this is too flamboyantly slow. Instead, let's talk about SIMD, single instruction multiple data. Particularly on ARM devices, we're going to look at the VMLAQ S32 instruction. That's vector multiply accumulate signed 32, which basically does 4 multiply accumulates at the same time. And the performance looks something like this. Now, what's interesting here is you haven't heard me say the F word yet. Not that F word. Floats. Why haven't I said floats? Well, the answer is they're too freaking slow. Everything that we've been doing so far has been entirely in fixed point numbers. Yes, the F in fixed point stands for fast, as opposed to the F in float, which stands for fast. I'm sure many of you have probably seen this meme before regarding programming abilities. I'd like to add my own meme into the meme pool for DSP programming. Okay, next up, the inverse FFT. Most people know what an inverse FFT is. You don't necessarily have to know how to calculate it, but you can probably use a library to implement this. The problem is, if we're trying to input data at 96 megahertz, when you factor 96, you get this 3 over here. And this 3 makes us sad, because it makes the FFTs a lot slower. If it were a power of 2, it would be way faster. So, do we use FFTW3, the fastest Fourier transform in the West? I don't think so. Too flippin' slow. Instead, on my laptop at least, I've got this awesome GPU here. May as well use that. Enter VKFFT. I was actually asking ChatGPT about VKFFT, and it told me all sorts of awesome stuff about a library that's maintained by AMD. It has this awesome interface. None of it's true. VKFFT has one thing going for it. It is really, really, really fast. Way faster than FFTW or any other implementation I've found. Unfortunately, the interface to it looks a little something like this. It was an absolute nightmare to get integrated into my code, but I did it. And here's an example of some stats coming out of my M1 laptop here. On the left, you can see the channelizer, over 100% real time. That means that we can actually decode all 80 channels of BLE, or all 40 channels of BLE in real time on a modern laptop. And I've also got this running on x64 as well, not just ARM. And if you've got a beefy Linux system, you can also do real-time decoding. Which brings me to the demo, everyone's favorite. Give me 1 second. I should probably use that. I'm sorry, if your Bluetooth is on, it's too late. Okay. If you'll bear with me. Alright, as promised, we're going to zoom to the bottom of our interface list. ICE9 Bluetooth, BladeRF 0. We'll go ahead and double click on this. And in theory, we should start seeing Bluetooth packets anytime now. Hey, those are BLE advertising packets and data packets. Yeah, clap! I'm going to filter out just the data packets. So these are all the data packets. You can see some unencrypted BLE packets from somewhere around here. This is a highly directional antenna, not a death ray. That's more chocolate master's thing. So in this part of the audience, somebody's got an unencrypted BLE device going bananas. This one is encrypted. You can see these control opcode nodes and L2 cap fragments. Those are encrypted data, but there were some unencrypted packets coming through. So yeah, try it. Download this code. Try it now. Buy a BladeRF. I hear they're in short supply right now, so get them while they're hot. What else do I have to say? Okay. Cool. Demo works. I'm going to leave you with some parting thoughts. This code is not done. These are all features that I'm working on right now. Classic Bluetooth sniffing is on the docket. Windows builds, as soon as I get around to them, really. There's nothing about this code that can't run on Windows. Channel hopping for the HackRF and USRP. USRP, despite being a more expensive radio, has less bandwidth than the BladeRF, so you cannot sit on all 80 channels at the same time, meaning that if you're trying to follow a connection, you will eventually have to hop to some different channel. I need to implement that for HackRF and BladeRF. That's going to be a little bit more work. Other VKFFT backends. So right now, VKFFT only runs on Macs with an M1. If you've got a Linux system, it will default back to FFTW3, so you're not exposed, but it's not great. And finally, other software-defined radios. Some related work. This is, I mentioned it earlier, this BLE sniffer runs on HackRF and USRP and BladeRF. It's a narrowband sniffer, but it does pretty well for what it is. It does do frequency hopping, if that's what you care about that. The original GR Bluetooth project by Dominic Spill and Mike Osman. And I actually found a couple papers. This was the closest paper to what I did. One GPU to snoop them all, a full band Bluetooth low energy sniffer. They promised to release their code open source, and they didn't. I'd also like to thank my sponsors, Nuand, the people who make the BladeRF. They sponsored me a BladeRF. Great Scott Gadgets sponsored me a HackRF. Edis, anyone else who makes software-defined radios, their name could be on this slide too if you want to add support for it. I've got some special thanks. I'm not going to read all of these out, but special thanks to everybody listed on here. And of course, thank you very much for coming. I'll put this slide up one more time, but that's it. Man, I promised Antrix that I would run long, and I'm actually below time now. So let's stretch that out with some questions. Anybody have questions? In the back. And I think there's a microphone that we're going to pass around too.
BladeRF with, I think, 56 megahertz bandwidth, do you think we'll still be able to cover?
Sorry, the BladeRF will, with 96 megahertz, will cover.
I think it was like 56
so this is
A9.
So the X89 and the X84 both support this new wideband mode. So you just need to firmware update your BladeRF and you can snip all of these.
Got it. Okay, thanks.
Is there any plan to incorporate error correction?
There is no error correction in BLE packets. So unless you're, well, what do you mean by error correction?
Well, that you mentioned that there would be errors in
so there
after the constitution.
So there are going to be a couple sources of errors. There's going to be random noise, which we can't correct for. We can just check the CRC on the packets and reject them if they're inaccurate. And then there's going to be processing induced errors that I just need to make my processing chain better. But I don't really think error correction enters into that because it's just not part of the Bluetooth protocol.
You mentioned it's probably pretty hard for a radio to sit on all the channels at once. So how do regular Bluetooth receivers do that?
So regular Bluetooth receivers have a priori knowledge of wherever the connection that they're a part of is going to be at any given time. So they just hop along at the right moment on the right channel, and voila, the data appears where they expect it to.
But if you're sniffing, you don't necessarily know that.
Exactly. And the other sniffers, like the Ubertooth and other NRF sniffer, the way they work is they sit on the advertising channel, wait for a connection to be established, copy out all the parameters from that connection, and hop along with it as though they were a legitimate device, just silently listen. But there are huge drawbacks to that approach, as I discussed earlier. Question here in the front.
Thank you for the talk. I want to just add for the previous question about the frequency hopping. I'm not a pro on that, but when the client received advertisement packet, is the hopping strategy it's like a predefined, or it's not like some kind of a encrypted, or what?
So in BLE, it's a pretty straightforward hopping pattern using the typical channel selection algorithm. You basically you get what's called a hop increment, which you add to the current channel, and modulo 37, because there are 37 data channels, you just hop according to that pattern. Now there are provisions for skipping certain channels because of collisions with Wi-Fi, for example. There's a second channel selection algorithm, but the channel hopping is not meant to be a security feature. It's meant to more be just avoiding collisions.
Thank you.
Question in the back.
Yeah, thanks for the talk. I really appreciated it. So there's one part that I didn't quite follow. You talked about punching on the clock recovery, and then you resolve your sample length. And then I think in the next slide you talked about as you're trying to discover like where the packet or like the header length is described. In your example, I think the header length was like 38, and then your sample length was like 34. How did you resolve those two to actually get like a valid packet part?
Like you mean the difference between?
Yeah, like there was like less data than actually the header was describing.
Yeah. So what the reason that is because our in this case it's
oversampled them a little bit, right?
Yeah, you just end up capturing a little bit of extra noise at the end or a little bit of noise at the beginning. We're just going close. We have the actual length from the BLE packet header, so we know the exact length of the packet. So we can just discard that noise that's at the end.
Oh, so you assume all the noise kind of aggregates at the end. You don't have to adjust your
No, yeah, it's all just going to be noise.
Okay, cool. Excellent.
Any other questions? Well, thank you very much. I've got stickers and business cards up here, or you can come ask me questions. But yeah, thank you.